The first speaker is Fabian, who is going to tell us about 50 years of X-ray astronomy.
Yes, in 20 minutes. So to remind you that X-ray astronomy started with a rocket flight by Riccardo Gicconi in 1962. And in that rocket flight, they found one point source, SCO-X1, which is the brightest source in the sky, and also a diffuse X-ray background. Martin Rees and Jim Felton, in a few years later, predicted the X-ray background was due to radio galaxies and predicted, therefore, it was like 40 sources per square degree or something, which could easily be, the granularity from that could easily be measured with a rocket flight. So that's what I did in my PhD. I started in 1969, and this was my detector down here. Okay, the detector's down here. This has got a delay, so it's annoying. And luckily, my data was telemetered down, and I was able to write a paper about how smooth the X-ray background was. I noticed ever since Martin Rees, in his papers, never makes numerical predictions. He makes sweeping predictions, but not, so many per square degree. Anyway, the X-ray background is here, and this is a deep image from XMM, and the cosmos field, 40 arc-minutes across, and you can see it's full of many point sources, most of which are accreting black holes in distant galaxies. It's also those red fluffy things, and they're clusters of galaxies. And I'm going to talk about both types of object. Let's go to clusters of galaxies, which come in two types. One are the cool core clusters, which are on the left, with big spikes in the middle. They're very bright in the middle, and the non-cool core clusters, which are not. And these cool core clusters are the ones I'm interested in, because what happens is the gas gets cooler and cooler towards the center, and as the temperature drops down, the density rises to sustain the pressure, the weight of the overlying gas, and that means that it just gets steeper and steeper, and the cooling time keeps dropping down. And this idea that the cooling time in clusters of galaxies was less than the age of the universe emerged from work by Susan Lee and others early in the 70s. And then in 1977, which was the year that Rees and Ostreicher and various other papers on galaxy formation from cooling of gas came out, that basically there should be cooling gas flow inwards, but the flow rates in these cool core clusters turns out to be hundreds of solar masses per year. And a big issue was what happens to that gas. And I'm going to pursue that a little. Here's the Perseus cluster of galaxies as seen by an amateur astronomer in the States, Jay Gaveney, a beautiful picture. And if I now overlay my Chandra image of the Perseus cluster, you see how well it goes on top. There's more baryons in the hot intracluster medium that there are in all the stars of all the galaxies within the cluster. And you also, I hope, can notice that many of the individual elliptical galaxies in the cluster show up with their little mini halos. But the most important thing is around 1275 in the center, it has jets that go north and south, blowing bubbles, and those bubbles are buoyant, and buoyant bubbles are seen either side like that. Such buoyant bubbles were predicted by Gullen Northover in the radio astronomy group here in the early 70s. But this is one of the clearest examples that was found early on with Chandra. And if we go to the center, the radio emission sits like that in these two bubbles, and the two bubbles are surrounded by a thick rim, which is of harder X-ray emission, which you might imagine as a shock, excepting if it is, it's an isothermal shock, but the density rises by 30% in this thick rim. And then we can go and look at yet another image of it, and you can see that shock-type feature, and you can see various other things, the two bubbles, those bubbles, and we can see red stringy things, which I'll come to later. But if you go from there to there, that's about 100 kiloparsecs. So these bubbles are galaxy-sized bubbles, and that one going from there to there is about 20 kiloparsecs, so really giant bubbles. And the bubbling excited many people, including me, And we thought that much of the cooling that was taking place was balanced by heating from these bubbles, because the bubbling clearly shows that the AGN is doing something. It's doing something galaxy-sized, and it's pushing the gas aside, and surely there's work done, PdV work done. And if you compare that in terms of cavity power versus cooling luminosity, it gives a good correlation for an astronomer. And so the whole idea about AGN feedback and how all of that is going on, and the idea that the cooling is suppressed by this was taking place. Julie later on will talk more about this, but I just remind you that this is actually a lousy correlation. And another issue is how is the energy distributed around the cluster, and it could be in terms of turbulent motions or sound waves. But then in 2016, the Hitomi satellite lasted just a few weeks, but it carried a microcalorimeter operating at 50 millikelvin, 50 millikelvins, and it was able to measure the spectrum of the hot gas in here. And as you can see, it's got very narrow lines, and we could measure the width of those lines, the dispersion. It was only 100 kilometers per second over most of this region, and the sound speed of the region is 1,000 kilometers per second. And that means that turbulent energy is only a few percent of the energy there. So I think there's probably sound waves happening there, but not everybody agrees. But there's also around 20 years ago, 25 years ago, when XMM was launched, and then 20 years ago, people were making spectra, this is with XMM RGS, of these cool regions, and finding that there was a lack of the clear emission lines from gas like iron 17. As the gas cools, it's going to recombine. When it gets neon-like, it produces iron 17. Iron 17 emission lines at 15 and 17 angstroms, which should be very strong, and they're not seen as being anywhere near as strong. So basically, most people concluded that cooling flows are dead and don't exist. Now let's go to the Centaurus cluster, a beautiful image Jeremy Sanders produced of this cluster. And when we look at the mass flow rate inferred in this cluster, it certainly seems to decline inwards down to below 1. But it means there's a lack of soft X-ray emission. But you can get rid of soft X-rays in many objects, and particularly AGN, through absorption. So is there any absorption taking place? I've then fitted many of the spectra over the last couple of years of these objects with an intrinsic absorption model where we've got multi-layers mixing up the cooling and emitting gas. And the energy from the gas will come out, absorbed energy will come out in the far infrared. But this is what it's like, the fit for with the XMM RGS of a hidden absorbed cooling flow of 16 solar masses per year, column density, total column density of 1.5 10 to the 22. It looks like that. And so it all fits very nicely. And we know that there's lots of absorbing material in this object because you can see it. It has this well-known dust lane and all this other stuff. And you can see how patchy it is in the center. And I've looked at many groups and clusters around, and there is plenty of absorbing gas in the middle of these objects. You can see it in these Hubble images. These are taken from published data over the last 20 years. These are the mass cooling rate versus column density and so forth. So I think these are common. So will too much gas accumulated? It's 10 to the 10 solar masses in Centaurus. In Perseus, it's going to be 10 to the 11 solar masses. What is too much? There's lots of cold molecular gas in these objects. We speculate, including Gary Ferland, who's here, that there are many ultra-cold clouds. The cooling time of the cold clouds is only 30 years. Perhaps they drop down to 5 or less. But the most obvious solution is there's a new mode of star formation taking place, a low-mass star formation, due to the high pressure. When you've got the high pressure, which is typically 10 to the 7 in these regions, it lowers the gene's mass. This was pointed out by Mike Durer in 1977. 1977, the key year in all of this, and I followed it up, and Gary as well. And maybe that's what's happening. We're forming lots of low-mass stars. And bear in mind that recently, like 15 years ago, Peter van Dokkum and others have found bottom-heavy IMFs in the middle of nearby elliptical galaxies. So the implication of this is that ellipticals are not dead. They may be red, but they're not dead. There's great activity taking place in the center. Going back to Perseus and on to molecular gas, Helen Russell, who's here, has done lots of work with ALMA on clusters. These are various clusters. That's an emission. This is an absorption. This is Abel 2597. You can see clear molecular absorption against the nucleus, and it's redshifted, which means it's moving inwards. And I can then calibrate how much feedback is operating and what its efficiency is from these comparing the cooling rates from images which cover 50 kiloparsecs compared to the RGS, which covers the inner few kiloparsecs. And when you're up here, this means heating is winning, feedback is really operating. But down here, particularly for ellipticals, it's not working. And also for these objects, it's not working. So what do these objects with 1,000 solar masses per year cooling rates look like? They look like this. They have cooling flows running wild at redshifts of 0.35. And there are other objects similarly highly excited. Moving on to AGN, this is an artist's impression of an AGN, and this is roughly what they may be like in the center when they're luminous, with a corona which is up there and which is producing the hard X-ray emission coming out to the observer. It then irradiates the accretion disk and produces fluorescence. And the fluorescent line, when coming from an accretion disk around a massive black hole, is going to show special relativistic effects and general relativistic effects, and you get this skewed line, which I and others predicted in 1989. And this is what it should look like. It should look like that if you look at these spectra, this is the reflection spectra as calculated by the late Randy Ross, who used to come very regularly every year. And this is what you get when you blur it. This was found in '95 with the first X-ray satellite with CCDs on it, a Japanese-American satellite, ASCA, and you can see the clear broad line. This is, Carolyn and I spent 93 in Japan, soon after ASCA was launched. This is Yasuo Tanaka, who led that particular bit of work. And this is taking you forward to the latest Japanese results from the CRISM satellite, which was launched last year. And this is, don't take photographs of this. This is new data. Here's the broad line in MCG6 and the Compton hump. And notice how similar the two are. But you see there's structure there. That structure is real because the extend resolution is 4.5 electron volts. The resolution here is about 160 electron volts. So that's what you get with a microcalorimeter. These are other similar broad lines seen with New Star, and Dom Walton, who's here, got a spectacular example from V404 SIG, which is a galactic binary that flared up. And let's go on. We can measure black hole spin. Chris Reynolds, who will be here later in the week, has assembled a diagram of black hole spin versus black hole mass. And Julia Sisgrains, who's sitting just in the front row there, has added to that on another object. And sometimes we get emission from this that comes from within 2 gravitational radii of the black hole. And you can see this is the emission in black with the red lines showing it being shifted. This in blue is unblurred emission, and that's because that's coming from colder, from gas further out. But when you analyze that, the reflection-dominated spectrum comes from within 2 gravitational radii. I'm now going to take you into the plunge region. The plunge region is right in the middle. You've got the accretion disk, and then it stops orbiting and falls in, plunges in at the innermost stable circular orbit. And this is work carried out later. I used the model produced by Andy Mummery from Oxford this year. And another source that flared up is Maxi 1820, which was followed with NICER on the space station. And NICER can look at very bright sources, and you'll find that the count rate up here is 60,000 counts a second, which is really rather nice. It first of all went into a hard state and then into a soft state. And this is what the stacking 6 new star data sets, and this is the ratio to a power law, plotting them there. This is what was analyzed from the hard state by Douglas Guisson. And then this is what I found when I went to the soft state data. So the black line is the hard state. The other lines, the colored lines, are in the soft state. When you look down here at these ratio plots to a power law, the black line peaks at around 6.5 kV, which is the iron line. But this other bump is peaking at 7.5 kV. It's not iron, it's not an atomic feature, it's an additional black body. So there's an additional slightly hotter black body in this object, and that slightly hotter black body at the center here is, I think, coming from the plunge region. And being a black body, I can work it out in terms of an area, and it turns out to be a ring that's only 2 or 3 kilometers wide at the ISCO, and the ISCO is out about 60 kilometers, because the mass of this black hole is around 8 solar masses. This is Andy Mummery's attempt at fitting it with his full Kerr model, and you can see that the dotted yellow line is what you get from inside the ISCO, and green is what you get from outside the ISCO, and that gives a beautiful fit to the data. So I think we are starting now to measure material at the ISCO, and the result for the innermost radius, which he was able to fit, gave about 5.5 Rg, and this is what Douglas got for the hard state, which is 5.5 Rg would be here. Now there are arguments you could make about exactly whether this is good to 1 Rg or not, but certainly we're starting to measure things very close to the black hole. And all you need is a relatively small stress, a mild stress at the ISCO. There's lots of debate theoretically about exactly what the stress at the ISCO should be, but it's, of course, a magnetized flow, and these may be the closest observations to the horizon of a low-spin black hole. Now, the legacy of all this work that we've carried out at the Institute, of course, is in the students and postdocs that have gone off elsewhere. And I've just made a list of places where there are still people from the X-ray group, the Cambridge X-ray group, and they include, I was looking him up today, the Director General of ESO happens to have spent 3 years here working on the X-ray background. So Xavier Barcons and I wrote a paper on the autocorrelation function of the X-ray background. So that's ACF and XB. So it's the autocorrelation of the X-ray background by XB and ACF. So you can find that on, and we also have got people in India. And also, of course, there are people, one's own students then go off and have students. And Jiachen Jiang, who's here, has done so in China. I haven't listed that, but these are the sort of first generation people. And just to finish, that Chandra advertised a legacy program late last year of having lots of long observations, or the possibility of long observations. They advertised there would be 6 megaseconds available for long observations. And I thought with my colleagues that let's have a go at this. We've been trying to get more time on the Perseus cluster. It's the brightest cluster in the sky. Let's make a hard X-ray image that's really going to be able to enable us to work out the equation of state of the intracluster medium. And we are delighted to have been awarded 3 megaseconds. Now, I really hope that Chandra survives to carry on doing this observation. Today is actually the 25th anniversary of the launch of Chandra, and Carolyn and I and our sons were at that launch when it was a night launch, and really spectacular shuttle launch with the first female commander, Eileen Collins, in charge, and it put Columbia into the perfect orbit and, of course, Chandra into a perfect orbit. Thank you for listening.